Alright, so today what we're going to be talking about are critical numbers and absolute extrema. So just to kind of give you an overview of what those vocabulary words mean, kind of talk about it. So first of all, we can have two different types of intervals. I can have a function that looks like this. Goes on forever, okay? This is called an open interval because it's not closed off anywhere. For this function that I have drawn, this point right here would be called a relative min. This point here would be called a relative max. This point right here would be called a relative min. See, I can't say anything about whether this is absolutely the lowest point. And I know it's really not because this point's lower. But because this is an open interval, this graph could come up and then it could turn back down again. So I don't know for sure that this is an absolute minimum. In order to find absolute maxes and mins, I have to have a closed interval. So I'm going to take this same kind of thing and I'm going to make it closed now. So just looking at a piece of the function. I'm only looking at it from here to here now. Well, now if I'm talking about a closed function where I'm calling this A and this B, the interval would be called the interval over A to B. Now this point is called an absolute max because I can see that's absolutely the highest point on the whole function. This point right here would be called an absolute minimum. It's the absolute lowest point on the function. Notice how this absolute max is occurring right here. This is where the slope changes. Look at the slopes here. This is positive, 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 positive slope. Then it's negative slope. So what is the slope right there at that max? 0. So that's what we're going to be looking at, is how to find something called a critical number. A critical number is whatever makes the slope equal 0. So these absolute extrema, they can only occur at a critical number or at an endpoint. We're going to be doing two things. We're going to be finding critical numbers, which are possible maxes and mins, and we're going to be finding absolute extrema, which are the absolute highest and lowest points on a closed interval. So, looking over here, this is just the formal definition. F of C, meaning the y value at C, is going to be the minimum, absolute minimum, of the function over this closed interval if that F of C is less than all of the others. It's just saying if it's the lowest point or the smallest value, it's going to be the minimum. If we have a maximum on an interval, that means that that point is going to be greater than all the other y's in that interval. So when we're talking about extrema, we're talking about any maxes or mins. This means all together. Extrema can be a hill or a valley, a high point or a low point. The high point is called the relative maximum. The low point is called the relative minimum. That's what we just talked about here. Extreme value theorem. Look at the difference. If a function is continuous on a closed interval from A to B, then f has both an absolute minimum and an absolute maximum on the interval. The absolute extrema must occur at the critical number or at the endpoint of the interval. That's what I was saying back here. This is an absolute max. It occurred at the critical number. The critical number is where the slope is 0. This is an absolute minimum. It occurred where we have an endpoint. So it has to be one of those two. Definition of a critical number. If our function is defined, then if f prime of c rather, if the derivative equals 0, or if the derivative is undefined for that c value, then c is a critical number. Remember again, a critical number is a possible extrema, possible max or min. Okay, so first of all, we're just finding any critical numbers. So like we just said here, we find the derivative and we set it equal to 0. But it would also be where the derivative is undefined. So I'm going to find this derivative. I could use the product rule, but I'm just going to go ahead and multiply it out. There's our function. To find the critical number, we take the derivative. And now we're going to set that derivative equal to 0. Solving this, I'm going to factor out a 2x. I'm finishing. I set 2x equal to 0. I set 2x squared minus 9 equal to 0. X equals 0 is a critical number. Solving this part. Take the square root. Okay, so these are going to be the critical numbers, these x values. Over the open interval, over the whole function, the only place where we can have relative extrema are going to be at 0 and at plus or minus 3 over radical 2. That's the only place where we can have high or low points. Okay, for number 2, now we have a trig function. We're trying to find any critical numbers. So, I have to think of this function, though, as the cosine of x squared plus sine x. We have to think of it that way. So let's go ahead and take this derivative. We have to think of this as u squared. U squared. So Jill, what's the derivative of u squared? And just if I said x squared, what's the derivative of x squared? Right, so the derivative of u squared is 2u. But now I have to do times the derivative of the u. Do we know what the derivative of cosine x is? Negative sine x. So I'm going to put my negative in front, negative sine x. That's the derivative of that term. I have to use the chain rule. Plus, what's the derivative of sine x, everyone? Cosine x. What do I do after we found the derivative? What do I do with it to find critical numbers? Set it equal to 0. The reason we do that is because those high and low points are going to occur where the slope, the derivative, is 0. So I have to set this equal to 0. Alright, what would I do to solve this then? Can I factor anything out of it? Cosine, so I'm going to factor out a cosine. And so I'm left with negative 2 sine x plus 1. So now I'm going to set this equal to 0. So solving this one now, think of your unit circle. We have to know, where does cosine equal 0? Cosine is that adjacent over hypotenuse, or x over r, however you want to think of it. This is quadrantal. We have to think, where is it that x is going to be 0 on that unit circle from 0 to 2 pi? Anybody know? Yeah, what do you think, Michael? Excellent. So those are going to be two of our critical numbers, pi over 2, 3 pi over 2. That's where the x value is going to be 0. See, this point's 1, 0. This point's 0, 1. This point's negative 1, 0. That point's 0, negative 1. Where the x is 0 is there and there. Solving this one, I'm going to have 2 sine x equals 1. I'm just taking this over, switching it around. So sine x would be 1/2. So now we have to think, where on the unit circle would sine or the y value be 1/2? Right now? Good. Page, pi over 6. And then do you know the other one? Pi over 6. Very good. So those are going to be our 4 critical numbers. The trig never goes away. It always comes back, just when we think we're finished with it. Okay? Questions there? All right, so to find critical numbers, again, we set that derivative equal to 0, or we could set that derivative equal to undefined, being undefined, but that wasn't necessary on these two. All right, so now we're going to talk about absolute extrema. It's the same kind of process, but now we have to substitute in. Because remember that the absolute extrema must occur at either the critical numbers or at the endpoints. So we have to find the critical numbers first. So derivative here. What's the derivative of this going to be, Madison? All right. So we're going to set that equal to 0. Solving that, I get x equals -1. Now, this is asking me to actually find the extrema. So to find the extrema, I have to plug this back into the function. So I'm going to find f of -1. So that means I'm going to do -1 squared plus 2 times -1 minus 4. So that's 1 minus 2, that's -1 minus 4 is -5. That was a critical number that I checked, but that was also an endpoint. So that's kind of good. See, I only have to test numbers in this interval. The only possibilities for maxes or mins are going to be at the endpoints or at the critical numbers. Well, this is a critical number and an endpoint, so I checked it, and I got -5 for the y value. Now I have to plug in +1, not because it's a critical number, but because it's an endpoint. So I'm going to plug that in. So 1 plus 2 is 3, minus 4 is -1. The only possibility for a high point or a low point, an absolute highest point or absolute lowest point, are these two y values. Which one of these, what's this one going to be then? Is that an absolute max or an absolute min? It has to be an absolute min, doesn't it? Because it's lower than this one. So I would say my absolute min is at -5. My absolute max is at -1. Now, I don't really want you using your graphing calculator to do these, but I want you to understand what it is we're actually doing there. So let's put this function in. We've got x squared plus 2x minus 4. I only want to look at this function between x values of -1. Actually, first let's look at the whole thing to begin with. So here's what the function looks like over an open interval. But now I'm only going to look at it from -1 to 1, because that's the closed interval I'm looking at. Here's the way it appears. So we want to know what's the absolute lowest point. Look what I can do. I can hit trace. I can follow this function. See how my absolute lowest point is occurring right here at -1? That's the absolute lowest. If I trace it and I want to find the absolute highest point, I mean, I could sit here and do this and not use calculus, but we're trying to use the calculus method. So if I want to find the absolute highest point on that, that's occurring right there at -1. That's my highest point. Do you understand what we're doing? All right, on number 4. I solved for a critical number because that could also be where I have a high or low point. See, if I go back and I look at this whole entire graph, if I look at an entire graph right here, this would be a critical number because it's going to be where the slope is 0. So I took the derivative and I set it equal to 0 to find out where the slope is 0, because that could be a high or low point. The endpoints. So you always have to plug in the endpoints and the critical number back into the original.
So you have to verify that the critical number is an endpoint from the higher endpoint.
Yeah, I have to plug it in. Guys, it just so happened in this case that this critical number was also an endpoint. It wouldn't have to be. Like, if our critical number had been 0, then I would have had to have checked -1, 0, and 1. See, I have to check the critical numbers and the endpoints. Okay? All right, let's go on to number 4 now. So on number 4, we have to take our derivative, and to do that, we're going to have to use the quotient rule. So I have to do derivative of the first times the bottom, using the quotient rule, and then minus the top, and then the derivative of the bottom is 1, all over the denominator squared. So simplifying this, I'm going to have x minus 2 minus x over x minus 2 squared, and that just gives us this. That's our derivative. So remember, whatever makes this derivative equal 0 and whatever makes this undefined would be critical numbers. Let's just jot this down as a critical number there. Does anything make the top equal 0? Is there any value of x? No. So I don't have a critical number based off of having this equal 0. But what value would make this undefined? 2. So 2 is a critical number. Now, to find out where I have high points and low points, what do I have to always check for sure? The endpoint. Because those cutoff points could be maxes and mins. So I have to check f of 3, and I have to check f of 6. I'm also supposed to check the critical number. But why do I not have to check it in this case? Yeah. It would be undefined, that's one reason. There'd be a vertical asymptote there. That's one reason I don't have to check it. There's another reason too. There's double. Yeah, I'm only looking between 3 and 6. This 2 is lower than that, so I don't even care about it. So there's 2 reasons why I don't have to check it. But I do have to check the endpoints. So I'm going to plug in 3. So plugging that, where do I plug it in? To the derivative or the original? Original, because I want to know the y value. So plugging that in, I'm going to have 3, just 3. Okay, plugging in 6 now. I'm going to have 6 over 6 minus 2 is 4, and that's 3 halves. So one of these has to be a high point, one of these has to be a low point, and so therefore my absolute max has to be 3, the absolute min has to be 3 halves. Just let me show you this graph, just to show you what's going on here. So here's what the entire graph looks like, okay? On this graph, there's not much really happening for me on the open interval, but if I look at it only between 3 and 6, now I'm just looking at this. And I was trying to find the absolute highest and the absolute lowest. See how if I trace it, I can see that my absolute highest point is right there, whoops, when x is 3, and then the absolute min is going to be down here at 1.5. So we're only looking at a closed interval of the graph to find this. Okay, any questions about it? So what are we going to be finding? How do you find critical numbers? Derivative equal to 0 or where it's undefined. And then to find absolute extrema, what do we have to check back into the original? Critical numbers and the endpoint. Good. All right, let's look over your homework now.